Wireless Attacks course. The Offensive Security Wireless Attacks course, also known as WIFU, is a course designed for penetration testers and security enthusiasts who need to learn to implement various active and passive wireless attacks. This course is primarily based on the wireless attack suite Aircrack-ng. This course was designed in an attempt to organize and summarize today's relevant Wi-Fi attacks. Hopefully, we'll manage to kickstart your WIFU abilities and get you cracking WEP and WPA using the latest tools and attacks in no time. The presentation of this course tends to be quite challenging, as it is very tempting to jump straight into the practical hacking methods. However, we quickly realized that a proper introduction of the terms and concepts was required to fully benefit from this course. The first few modules will provide the basic overview of the wireless arena and get you familiar with the technical environment. In further modules, we'll discuss and practice hacking methods and techniques. I can promise you that the first couple of chapters in the course manual are a bit boring, with lots of definitions, explanations, acronyms, packet dumps, and diagrams. However, without a thorough understanding of the basics, true WIFU is not achieved. Please bear with us the first few chapters. Do your best not to skip them. It really is worth it. The movie presentations do not include the technical information in the first few chapters. Please take the time to read over the first few chapters and get familiar with the terms and concepts before actually trying these attacks. Let's take a look at our wireless interfaces and get familiar with our environment. I'll run iwconfig to see our wireless interface status. I currently have an Alpha Networks Realtek USB card connected, and it is currently configured as WLAN 0. This card uses the R8187 drivers, which have been patched for wireless injection. iwconfig also shows us that our wireless interface is in managed mode, and we are not associated to any access point. We can see what driver was loaded for our wireless interface by viewing the output of the dmessage command. So that's dmessage, and we will pipe that into grep, and we'll look for 8187. Based on the fact that there are no errors present, we can assume that our wireless interface is ready for use. Although Alpha cards are very popular in wireless hacking, some VMware environments have issues with the RTL8187 MAC 802.11 driver, where RFKill shuts down the wireless interface soon after it is loaded. If you encounter this issue, please refer to your lab guide for tips on how to resolve it. In 2007, the Linux wireless stack was changed from the older IEEE 802.11 stack to the newer MAC 802.11. Most of the wireless drivers in our attacking system generally use the stock kernel drivers patched for injection, meaning that most drivers are based on the MAC 802.11 stack. There are some exceptions to this, such as the Realtek 8187 Edman Wi-Fi NG IEEE 802.11 drivers, which are also included for extra compatibility with some older cards. The MAC 802.11 drivers generally support a single main interface called WLAN 0. This interface controls multiple virtual access points, or VAPs, which are shown to us as MON interfaces. Each VAP can be in a specific mode which cannot be changed. This allows us to have more than one VAP running simultaneously. In order to change a VAP's mode, you can use the IW command or use the Airmon-ng command to destroy it and then recreate it. Remember that all of this is relevant only to cards using the MAC 802.11 drivers. We are paying particular attention to the Realtek 8187 drivers, as they are the ones that are used for the extremely popular Alpha USB wireless card. My Alpha currently has the legacy IEEE 802.11 R187 driver loaded, rather than the newer Mac 802.11 one. A quick way to determine if you are using IEEE 802.11 is to attempt to use the iwlist command. This command fails because IW is only supported for wireless cards using the Mac 802.11 drivers. To switch over to using the Mac 802.11 driver, I will first unload the current driver with rmmod R8187. And I'll then load the newer Mac 802.11 driver with modprobe RTL 8187. Running iwconfig again will show us that the driver has been loaded correctly. Now, if I run iwlist again, we should receive a lot of detailed information about the wireless interface. I'll run iwlist, and we'll pipe this into the less command. Excellent, so our switch over to the Mac 802.11 driver was successful. Now that we can load and unload our required drivers, let's see what it takes to put our wireless card in promiscuous or monitor mode. The Mac 802.11 driver stack uses the userland IW program to manually configure and poll the wireless drivers. Before we actually put our card into monitor mode, let's take a look at some useful IW commands. To get a list of wireless access points that our interface can detect, we can use the iwscan command, and I will grep for SSID to get a clearer view of the access point names. So that's iw, dev, and the name of our interface, WLAN0, scan, and we will grep for SSID. And these are all of the access points currently within range. To see a listing of wireless channel numbers and their corresponding frequencies, we can run iwlist WLAN0 frequency. And to see what channels the access points within range of us are transmitting on, we can run iw dev WLAN0 scan, and we will egrep ds parameter set, and we will pipe for SSID. Knowing what channel a specific access point is transmitting on is quite useful when it comes to filtering out background noise, as we will see later on. Let's now use the iw command again to add a Mon0 VAP that will be in monitor mode. We can do this by running iw dev, our wireless interface name, WLAN0, interface add Mon0, this will be our monitor mode interface name, type monitor. I'll need to bring this interface up now with ifconfig Mon0 up. Running iwconfig again should show us that we have a new Mon0 interface. And here is our new interface name, and we can see that it is indeed in monitor mode. Let's just verify that our card really is in monitor mode by using TCP dump. So we'll run TCP dump -i and our monitor mode interface name, Mon0, -s, 65,000, this is the snap length, and -p. So in TCP dump's output, we can see lots of traffic, mostly beacons and client probes from all of the access points in our area. So we know that we are in monitor mode successfully. And once we have finished with our VAP, we can delete it by running iw dev, the interface name, Mon0, interface del. And now our monitor mode interface has been destroyed. IEEE 802.11 drivers do not use VAPs to get into monitor mode, but use their main interface instead, with the exception of legacy MAD Wi-Fi NG drivers. I'll begin by unloading the Mac 802.11 drivers with rmmod RTL 8187. And I will load up the IEEE driver instead, with modprobe R8187. We can see that we have our WLAN0 interface back again. Once again, before putting the interface into monitor mode, let's use the iwlist command to see what access points are visible. With iwlist WLAN0 scanning, and we will grep for ESSID. Let's parse this output a little more to see the channels that each access point is transmitting on. With iwlist WLAN0 scanning, and we will pipe this into egrep, ESSID, and channel. Great. Now we'll use the iwconfig command to put the wireless card into monitor mode, this time on channel 3. So I will run iwconfig WLAN0 mode monitor channel 3. And I will bring the interface up. And now the iwconfig command shows us that our interface is indeed in monitor mode. Again, I'll run tcpdump to verify that our card has been successfully set to monitor mode with tcpdump -i WLAN0 -s 65000 -p. And looking at tcpdump's output again, we can see that we are sniffing traffic from multiple access points in and around channel 3. To take our card out of monitor mode, I will run iwconfig WLAN0 mode managed. And we can see that once again our wireless card is back in managed mode. Aircrack-ng is a suite of tools for auditing wireless networks. The suite includes a network detector, a packet sniffer, a packet injector, a WEP and WPA cracker, and several other useful tools. Aircrack can crack wireless WEP and WPA pre-shared keys using various methods such as the FMS, PTW, and brute force attacks. The first tool in the Aircrack-ng suite that we will examine is the utility script called Airmon-ng. Airmon-ng is used to enable and tear down monitor mode interfaces on wireless cards. Entering the Airmon-ng command without any parameters will show all of your current interface statuses. So let's try that out. I'll enter Airmon-ng. We can see that Airmon-ng has detected our WLAN0 interface with its Atheros chipset and the driver that is currently being used. Before we put our wireless interface into monitor mode, there may be processes running on our machine that can interfere with various attacks. To see any problematic processes, we can type in Airmon-ng check. And we can see that Airmon-ng has detected a number of processes that could be problematic for us. We can have Airmon-ng automatically terminate these processes for us by running Airmon-ng check kill. And now if we run Airmon-ng check again, we should see that there are no problematic processes. Excellent. Now let's go ahead and put our wireless card into monitor mode. I'll type in Airmon-ng start WLAN 0. And we can see that monitor mode has been enabled on a new interface name of Mon0. To disable monitor mode, we can type in Airmon-ng stop Mon0. And here we can see that the Mon0 interface has been removed. To place the card in monitor mode set to a specific channel, we can add the required channel number at the end of the command. This will make sure that Airmon-ng puts the card into monitor mode on that specific channel. For example, to start monitor mode on channel 3, I'll type in Airmon-ng start WLAN 0 3. Now, if I run iwlist mon0 channel, the Mon0 interface has been set to channel 3. Starting monitor mode on a particular channel is very useful, as it helps to filter out the access points in the vicinity that we are not interested in, and is especially useful in heavily populated areas. Airodump-ng is used for packet capture of raw wireless frames and is particularly suitable for collecting WEP initialization vectors for later use with Aircrack-ng. If we had a GPS receiver connected to this computer, Airodump-ng would also be able to log the coordinates of the found access points for later reference. This GPS data can then be imported into a MySQL database and online maps to map the locations of the access points geographically. Before we run Airodump-ng and start sniffing, we need to make sure that our card is in monitor mode. Of course, the easiest way to do that is by using Airmon-ng. Airmon-ng start WLAN 0. Next, we'll run Airodump-ng with our monitor mode interface name as a parameter and see which networks are within reach of our wireless card. So that's Airodump-ng Mon0. Airodump-ng presents a wealth of information to us. Let's stop the capture here and examine a few of the key fields. The BSSID field contains the MAC addresses of the access points that are visible. The data field is the number of initialization vectors that Airodump has captured so far. The numbers per second field shows the rate at which the data packets are being collected. The ENC field displays what encryption type is on use in the access point. The cipher column displays what cipher that is detected on the encrypted network. And the auth field displays the authentication protocol in use. Down in the lower portion, the station field contains the MAC addresses of the visible clients. For a more detailed description of all of the Airodump-ng fields, please refer to your lab guide. Now, since there are so many access points in my area, I'll stop monitor mode on my wireless card and restart it on channel 3, which is the channel number that the Wi-Fi access point is transmitting on. So I will stop monitor mode with Airmon-ng stop Mon0. And I will restart it again on channel 3 with Airmon-ng start WLAN 0 3. Now let's start up the Airodump capture again and see the difference. So I will run Airodump-ng -c followed by the channel number of 3 mon 0. There, that's much better. So we can see that Airodump-ng has detected a wireless client that is connected to our Wi-Fi access point. Again, the station column contains the MAC address of the client, and the BSS ID column is the MAC address of the access point. Let's start a file containing this information. We will call this file info, and we will use it for easy reference when we start attacking things later. So I will echo AP equals, and I will copy and paste our MAC address of the access point, and we'll shove this into info. Then we will echo vic equals, and I will copy and paste the MAC address of the victim client, and we'll append this to the info file. We will also want to add our own MAC address to this file. We can get our MAC address by using the MacChanger utility. So all we need to do is type in MacChanger -s followed by our interface name, mon0. So I will echo mon equals, I will copy and paste our own MAC address, and append this to the info file. I'll just cat this file to make sure I got things right. Excellent, so let's proceed. Now that we have covered some of the basics, let's begin sniffing some wireless traffic on the unencrypted wireless network. To help filter out any additional networks in our area, we will use Airmon-ng to start monitor mode on channel 3 by running Airmon-ng start WLAN 0 3. Now that we've put our card into monitor mode on channel 3, we can run Airodump-ng with some more advanced parameters. So I will run Airodump-ng -c followed by the channel number 3 --BSS ID followed by the MAC address of the access point. I will grab this from the info file. -W, followed by the file name we wish to save the capture to. We'll call it clearcap, and our mon0 interface name. Now, while Airodump is running, let's try to generate some clear text traffic by authenticating to an FTP server from a different machine on the wireless network. So I will switch over to my Windows XP victim machine, and we can see that we are connected to the Wi-Fi access point with a very good signal. I will log in via FTP to another system on the wireless network. And I'll enter in the username of OffSec and the user's password. So we've successfully connected. I'll just exit out of this, and we'll return to our attacking machine. Let's stop our Airodump capture and open up the capture file in Wireshark to see what's inside. So I'll simply run Wireshark, followed by our capture file name, that will be clearcap. I will sort the dump by protocol to hopefully make it easier to find the FTP transaction. This looks like it here, so I'll just right-click and follow TCP stream. And here we have, in plain text, the username and password as it traveled across the unencrypted network in clear text. It would be wise to keep this exercise in mind the next time you contemplate connecting to that open network at the coffee shop or airport while using clear text protocols such as FTP, SMTP, and POP3. Aireplay-ng is primarily used to generate or accelerate traffic for the later use with Aircrack-ng. Aireplay-ng supports various attacks, such as de-authentication, packet injection, fake authentication, interactive packet replay, and more. Let's quickly type in Aireplay-ng and see what options we have. In this section, we can see the filter options. These are various command options which will help us single out our victims or our clients. And in this section, we have our replay options, which allow us to control the rates and methods of our replay attacks. An interesting section to note are the source options. Notice that Airreplay allows us to obtain packets from two sources. The first source is a live flow of packets from our wireless cards. The second source is from a pre-captured PCAP file. Reading from a file is an often overlooked feature of Aireplay-ng. Remember that you can save any packet capture for later use. And this final section lists the various attacks that Aireplay-ng supports. The first, and perhaps most critical Airreplay option we will explore, is the injection test. The injection test determines if your card can successfully inject wireless packets and measures ping response times to access points. The percentage of responses received gives a good indication of the link quality. If you have two wireless cards connected, then the test can also determine which specific injection attacks can successfully be executed. The basic injection test lists the access points in the area which respond to broadcast probes, and for each of them, performs a 30-packet test which measures the link quality. This connection quality quantifies the ability of your card to successfully send and receive a response to the test target. Let's try running these tests and see how they work, beginning with the single card injection test. To begin, we first, as always, need to put our card into monitor mode by running Airmon-ng start WLAN 0. Then, we run Aireplay's injection test, test 9, using the monitor mode interface, with Airreplay-ng -9 mon 0. Excellent! Our single card test tells us that injection is working. The card-to-card injection test is a far more robust check, which also tests for the ability of the card to implement various air replay attacks, such as fragmentation attacks. I have connected a second wireless card to my computer that has been set to monitor mode, so we will run the test using the second card as the receiver and the first as the transmitter. So I will run Airreplay-ng -9 for the injection test, -I, and our receiving card, WLAN1, Mon0. Wonderful. So according to the results, all of the tests passed. So hopefully, we should be able to perform all of Airreplay's attacks with this card. Now that we have successfully tested the injection capabilities of our wireless card, let's dive right in and start attacking encrypted wireless networks. Although web encryption is a serious no-no for the tech-savvy individual, for various interoperability reasons, many corporate environments are still using web encryption in their wireless networks. In conducting the following exercise, we will have the opportunity to cover several of the available attack modes in the Aircrack-ng suite. I have reconfigured my wireless router to enable web encryption with a simple web key of AABBCCDDEE, and I have my victim Windows XP client associated with it. So let's proceed with our attack. Take this opportunity to cover Airreplay's Attack 1, which is called the Fake Authentication attack. The Fake Authentication attack allows you to associate with an access point using either of the two types of web encryption, the open system and shared key authentication. Although not strictly required, we will start most of our attacks in this course with a fake authentication request to the victim access point, in order to be able to communicate with it. This attack is useful in scenarios when there are no associated clients and you need to fake an authentication to the AP. Do note that fake authentication attacks do not generate ARP packets, so don't try to use this attack in order to capture ARP files. Let's start sniffing the network and see what happens when we try a fake authentication attack. So we'll quickly fire up Airmon and put the interface in monitor mode on channel 3, which is the channel that our access point is on. In your lab environment, you will set this to the specific channel that your access point is transmitting in. So I will run Airmon-ng start WLAN0 3. And we'll also start our Airodump session right here running Airodump-ng -C3 for the channel number of our access point, --BSSID, followed by the MAC address of the AP. I will copy and paste this from our info file. -W, followed by the file name of WEP1. This will save the capture file to disk, and we will be sniffing on our Mon0 interface. We will want this packet capture saved to disk so that we can pass it to Aircrack-ng later and break the WEP key. So now we have Airodump sniffing on channel 3, and we currently see the beacons that are being sent from the access point, and we have the client we configured earlier associated to the AP BSSID. Now I'll begin the fake authentication attack, which will actually authenticate my MAC address to the access point and allow me to send traffic to the AP. If you are not authenticated to the access point, your traffic will be rejected. To perform the fake authentication, we'll type in Airreplay-ng -1, which represents the fake authentication attack, 0, which is the reassociation timing in seconds, -e, followed by the access point's ESSID, which in our case is waifu, -a, followed by the MAC address of the access point. Again, I will paste this from the info file. -h, followed by our own MAC address. And we want to do this all through the Mon0 interface. Now let's run this and keep an eye on the Airodump window and see what happens. And look at that! We've had a successful authentication, as we can see up in the Airodump output. Notice that Airodump seems to think that our MAC address is a new client connected and associated to the access point. Let's take a quick look at a Wireshark capture and see what happens during the fake authentication attack. The entire fake authentication takes place with only 4 packets. In the first packet, our wireless card sends an open system authentication request to the access point. In the next packet, the AP responds with a status code of successful. Our card then sends an association request to the ESSID of waifu. And again, the access point responds back with a status code of successful. So just as easy as that, we have performed a fake authentication and association with the AP. So this was the fake authentication attack. Remember that many of the attacks against wireless networks actually need to start with the fake authentication attack in order to allow us to later send packets to the access point without them being rejected. If the fake authentication attack is never successful for you against a particular AP, then MAC address filtering may be in use. The access point will only accept connections from the MAC addresses in a specific access list. In situations such as these, you will need to obtain a valid MAC address by observing the traffic using Airodump, identify a wireless client, and impersonate its MAC address once you see that it has gone offline. If you are having other problems with fake authentication, please check the lab guide for further information. Authentication attack, Attack 0, sends disassociation packets to one or more wireless clients currently associated with an access point. Disassociating clients can be useful in several situations. For example, when trying to recover a hidden SSID, or when you're trying to capture WPA or WPA2 handshakes by forcing clients to re-authenticate. Another nice feature is that in certain environments, such as the one we currently have configured, disconnecting the client can actually force an ARP packet to be sent when he reconnects. These ARP packets are a needed commodity, as we'll soon see. As an initial demonstration of the de-authentication attack, I will de-authenticate the client station while connected to it over VNC on a wired connection. This will allow us to observe our wireless client as we execute the de-authentication attack against it. So I will open up another terminal window, and I will use the VNC viewer to connect to the victim client. So we can see that this wireless client, our victim, has 2 network interfaces, one wired and the other wireless. I am currently connecting to it via its wired interface at 10.0.0.100. This is the wireless interface which is connected to our access point. This wireless client is connected to our Wi-Fi network with a very good connection. To demonstrate the effectiveness of the de-authentication attack, I'm going to ping our access point indefinitely while we run it. And I'll just slide this VNC window off to the side. And now I'll run the de-authentication attack by typing in Aireplay-ng -0 to specify the de-authentication attack, 1, the number of de-authentication packets to send. If we were to type in 0 here, by the way, it would continue to send the de-authentication indefinitely. Next we need to specify -a, followed by the MAC address of the access point, -c, and the MAC address of the victim client, all through mon0. Now before I actually execute this command, let's keep an eye on our Windows XP victim. Notice that it is well connected and it is currently pinging the access point through the wireless interface. So I will press Enter here to launch the attack. Now notice what happens. We were pinging everything and everything was just fine. And suddenly, we were disconnected from the network and were unable to ping the AP. And then, after Windows XP automatically recovers, we are successfully pinging again. Now during this reconnecting stage, there is a high probability that an ARP packet was sent to the AP. And if this were a WPA network, the client would also have to re-authenticate. And let's take a quick look at a Wireshark capture and see what happens in this attack. So in our Wireshark output, we can see the big flood of de-authentication packets that were sent to the victim client. And then, as it recovers, just as when we perform the fake authentication, the client performs an authentication and an association back to the access point. The ARP packets that we have discussed when the client reconnects is critical because in order to crack WEP encryption, we would like to capture the ARP packets in order to play them back and generate a large number of weak initialization vectors. Let's move on to the next attack we will need for this exercise, Aireplay's Attack 3, the ARP Request Replay attack. The classic ARP Request Replay attack is the most effective way to generate new initialization vectors. Of all the attacks Aireplay has to offer, this attack is probably the most reliable of them all. Aireplay-ng listens for an ARP request packet, and once found, retransmits it back to the access point. This in turn causes the access point to repeat the ARP packet with a new initialization vector. Aireplay will then retransmit the same ARP packet over and over again, and with each packet sent, the access point will repeat this packet with a new initialization vector. By collecting enough of these initialization vectors, we'll later be able to crack the WEP key using Aircrack-ng. If you are unfamiliar with ARP requests, please check the lab guide for more information. Let's set up our environment to demonstrate the ARP Request Replay attack. With this attack, Airreplay will listen specifically for ARP packets. These ARP packets are a bit smaller than normal packets and therefore can often result in much faster injection rates. Looking back at our running Airodump session, we can see that the data packets are increasing at a very slow rate. We can also see that our fake authentication session has timed out again, so we will run attack 0 to re-authenticate to the AP. So I'll run Airreplay-ng -1 0 for the fake authentication attack, -e waifu for our access point's ESSID, -a followed by the MAC address of the access point, -h followed by our own MAC address, through the Mon0 interface. And our Airodump output shows us that we have again successfully performed the fake authentication to the AP. Although the ARP replay attack theoretically does not require you to perform fake authentication with the access point, there is a known bug in the MAD Wi-Fi NG drivers, and in order for these attacks to work while using MAD Wi-Fi NG, we must actually fake authenticate before each and every attack. Performing a fake authentication does not adversely impact the attack, so it's a good habit to get into regardless of what drivers your card is using. So let's start the ARP request replay attack. So I will enter Airreplay-ng -3 for the ARP request replay attack, -b followed by the access point's MAC address, -h followed by our MAC address, through Mon0. So at this point, we are keeping a close watch on the Airodump console. In particular, the data field, which is where we can see the number of weak initialization vectors that have been captured so far. So now we are waiting for an ARP request to appear on the network. Now this may actually take some time. If it's not happening quickly enough for you in your lab, then you can try to send a de-authentication attack to one or several clients and hope that they send some ARP packets back when they reconnect to the network. You can also force the issue in your lab by physically going to one of the victims and pinging a non-existent IP address. So let's hurry this along and send a de-authentication attack against a connected client. So we'll run Airreplay-ng -0 for the fake authentication attack, -a and the access point MAC address, -c and the victim client's MAC address, through the Mon0 interface. Wonderful! So a packet was received and is automatically being replayed. And we can see in the Airodump window that the data packets with weak initialization vectors are growing very rapidly. Once we have captured enough of these weak IVs, we will hopefully be able to crack the WEP key in use on the access point. Move on to the final tool for this attack, Aircrack-ng. Aircrack-ng is a wireless WEP and WPA PSK cracking program included in the Aircrack-ng suite. Aircrack-ng can recover a WEP key from a captured dump once enough encrypted packets have been captured with Airodump-ng. Aircrack-ng can use the PTW approach, the FMS correct method, or a dictionary file in order to crack a WEP key. Now just to make it extremely clear, the ARP packet injection technique we have used is only relevant for WEP-enabled networks. With WPA, since the encryption method is completely different, injection techniques will not be effective. Basically, this leaves us with capturing the WPA handshakes and attempting to crack the pre-shared keys using brute force or dictionary attacks. So let's take a look at Aircrack and talk about some of its more advanced options. By default, Aircrack-ng resorts to the PTW method in order to crack WEP keys. One main constraint of the PTW method is that it only works with ARP request reply packets and cannot be used with other types of traffic. In practical terms, what this means is that when we use Airodump to capture our traffic, we should not use the --IVs option. Let me just clarify what I'm talking about. One of Airodump's options is --IVs that will cause it to save only packets which contain initialization vectors. If we want to use Aircrack's PTW attack, it is vital that we do not use this option. Otherwise, the PTW attack will not work. In a nutshell, the PTW method extends Client's attack and optimizes it for usage against WEP. For more information about the PTW attack, please check the lab guide. We also mentioned the FMS-Correc method. The FMS-Correc method incorporates several cracking techniques. Using statistical mathematics, the possibility that a certain byte in the key is correctly guessed goes up by as much as 15% when the right initialization vector is captured for that particular byte. Certain initialization vectors leak the secret WEP key for particular key bytes. This is the fundamental basis of all the statistical techniques. So let's go ahead and crack our running dump, look into Aircrack's options, and try to decipher Aircrack's cryptic output. So I will simply type in Aircrack-ng -0, which is an undocumented feature of Aircrack that provides us a nice colorful output, followed by the capture file name. And this is the Aircrack cracking output screen, and we can see that it has already cracked our simple WEP key. Let's try to make sense of this cryptic output. The display is arranged in a variety of columns. In each column, we can see each byte of the key that has been guessed, along with the votes that the particular byte has received. And we can see that Aircrack-ng has voted AA and BB highest, along with DD and EE. But notice here that 0C was voted highest. So basically, what happened is that based on these votes, Aircrack-ng started brute forcing all other options with slightly lower possibility. And at the end of the day, Aircrack-ng managed to verify the key is what it was set to be. And it has a 100% probability of being decrypted correctly. So we can actually see that this cryptic output does make some sense. Another cracking option that Aircrack has to offer is the dictionary attack. Aircrack-ng can use a dictionary brute force attack in order to discover a WEP or WPA key. The dictionary file needs to contain either ASCII or hexadecimal keys, but not a mixture of both. This file can then be used as an input source to Aircrack-ng, and the program will test each key to determine whether it is correct. In fact, the dictionary attack is the only method to crack WPA pre-shared keys. Another great feature of Aircrack-ng, as we have seen here, is that you can run it against a capture file while Airodump is still running its capture. Aircrack-ng will auto-update when new initialization vectors are available and include them in its statistical calculations. As our attack from start to finish, we began by placing our wireless card in monitor mode on our desired channel, with Airmon-ng start WLAN 0 followed by the access point channel number. We then started a capture dump using Airodump-ng, saving the capture to disk, with Airodump-ng -C followed by the access point channel number, --BSSID and the AP MAC address, -w and the capture file name -mon0. We then conducted a fake authentication attack on the access point with Airreplay-ng -1 0 -e and the AP ESSID -a and the MAC address of the access point -h and our MAC address mon0. At this point, we also launched the ARP replay attack with Airreplay-ng -3 -b and the AP MAC address -h followed by our MAC address mon0. In order to speed up the chance of getting an ARP packet, we performed a de-authentication attack against the connected client with Airreplay-ng -0 1 -a and the AP MAC address -c followed by the client's MAC address mon0. Once the client reconnected to the network and we started capturing initialization vectors, we cracked the WEP key using Aircrack-ng by running Aircrack-ng -0 followed by the capture file name. In the majority of situations, cracking WEP is accomplished by attacking the access point by generating a packet that, when replayed, causes the access point to create new packets with new initialization vectors. In this module, we'll be looking at our WEP cracking approach from a slightly different angle. Rather than attacking the access point, we're going to try to attack a connected client to force it to create new packets with new initialization vectors, rather than the access point. This scenario is extremely useful, especially if we encounter some access points with specific restrictions, or if we are within range of a connected client, but not the access point itself. There are actually several ways to execute this attack, so please check the lab guide for more information. Let's start getting things ready to conduct our attack. I'll begin by placing my wireless card into monitor mode on channel 3 with Airmon-ng start WLAN 0 3. Now I'll start Airodump-ng, filtering on channel 3 and our target BSSID, and we'll save the packet capture to a file called Client WEP. And we'll send this out through our mon0 interface. So I will run Airodump-ng -c3 -BSSID, and I will paste in the access point's MAC address, -w, and the file name of Client WEP, and we'll be sniffing on our mon0 interface. Now, even though it is not required for this attack, I will launch a fake authentication attack against the target network, as having our MAC address associated with the access point tends to make this attack more reliable. So I will enter in Airreplay-ng -1 0 for the fake authentication attack, -e followed by the ESSID of the access point, waifu, -a and the AP's MAC address, -h followed by our MAC address, and we'll send this out through the mon0 interface. So we've successfully associated with the access point, so let's proceed. We'll be attempting this scenario using Airreplay's Attack 2, the interactive packet replay attack. This attack allows you to choose a specific packet to replay back against the target network. Basically, we're looking for a packet that when sent to the client will cause it to respond. ARP request packets are the perfect candidates for this, as a client must respond to an ARP packet directed to it. In order to use the interactive packet replay successfully, a deeper understanding of wireless packet flow is required. We can't simply capture and replay any packet, as only specific packets can be replayed successfully and cause IV generation by the client. To achieve this, we need to select a packet which will be naturally successful in generating initialization vectors. There are two characteristics that a packet needs to have in order to naturally work. The first is that the packet must be destined to the broadcast address, and secondly, the packet must be going from the wired network to the wireless network, which is a packet with the from DS bit flag set to 1. It just so happens that ARP request packets have these necessary characteristics. So an ARP request packet would be considered a naturally successful packet. However, we can't just use any old ARP request. It must be an ARP request for the specific client that we're targeting. We can use Aireplay-ng in order to screen down the packets we receive and try to identify exactly the packets that we need. So I will enter in Aireplay-ng -2 for the interactive packet replay attack, -b followed by the MAC address of the access point. I will grab this from our info file. -d and set the destination address to the broadcast address. -f1 to filter for packets with the from DS bit set. And we'll use the -m and -n flags to set the minimum and maximum ARP packet sizes. And we'll be sending all of this through our Mon0 interface. So now that we have launched our interactive packet replay attack, we begin waiting for packets to arrive that comply with our specified criteria. We might actually need to try several packets until this attack works. Alright, so we've captured a packet with the from DS bit flag set and a broadcast destination address. Theoretically, if we type yes here, then what we'll see is this data field increasing rapidly as the access point generates more packets with weak initialization vectors. Collecting enough of these weak IVs will allow us to crack the WEP key. So let's try injecting this first packet and see what happens. Absolutely nothing. So we'll stop this injection and we'll try to choose our packet more carefully. Now what I'll do is I will ping the victim machine from another client on the wireless network to try to force an ARP request directed at our client. I'll use the connected Windows client to ping 192.168.1.100, which is the IP address of our victim client, and let's see what happens. So hopefully this is the correct packet that we need. So let's start injecting this. Excellent, so we can see that the client is experiencing a lot of traffic and is generating a great number of initialization vectors. Enough initialization vectors captured to at least start our Aircrack attack on the capture file. Even if Aircrack can't crack the key right away, it will automatically refresh periodically and keep trying. This time, we'll run Aircrack with some extra options to demonstrate some more of its features. So I'll run Aircrack-ng -0 to give us the colorful output, -z for the PTW attack, -n64 for the number of bits in the WEP key, and we will provide it with our capture file name. Well, that was extremely fast. Cracking our simple WEP key was accomplished instantaneously. Now notice these files which have been created here. These two files have been created during my ARP packet injection attempts. Remember when we first went over Airreplay that we saw that it can also accept a file as input. So we could repeat this attack very easily simply by using the already captured ARP file and re-injecting it into the network. So I will minimize this window and cancel our current injection attack. I will copy this file name, and let's try re-injecting this capture back to the network. So I will type in Airreplay-ng -2 for the interactive packet replay attack, -r to pass it an input file name, and we will paste in the file name of our capture, and we'll send this through mon0. Now as I press enter here, we'll keep an eye on the data field in our Airodump output. I'll select yes to inject this packet, and there we go. Once again, we are injecting data into the network. IVs are increasing rapidly, and this time we are actually using the file which was saved on our disk and didn't have to wait on the network to find a good file. So once again, to reiterate, this is a very nice feature of Aircrack that is frequently neglected. In summary, we began by placing our wireless card in monitor mode on our desired channel with Airmon-ng start WLAN 0 followed by the access point channel number. We then started a capture dump using Airodump-ng, saving the capture to disk with Airodump-ng -c and the access point channel number --BSSID and the AP MAC address -W and the capture file name mon0. We then conducted a fake authentication attack on the access point by running Airreplay-ng -1 0 -e followed by the AP ESSID -a followed by the access point's MAC address -h followed by our MAC address mon0. We then launched Airreplay's interactive packet replay attack by running Airreplay-ng -2 -b and the AP MAC address -d and set the destination address to the broadcast address -f1 to filter for packets with the from DS bit set -m68 -n86 to set the minimum and maximum ARP packet sizes, and we sent this through the mon0 interface. Once we were injecting packets successfully, we ran Aircrack-ng with Aircrack-ng -0 for the colorful output, -z for the PTW attack, -n64 for the number of bits in the WEP key, followed by the capture file name. WEP cracking attacks we have covered so far have been nice and straightforward. But what happens if there are no wireless clients on the network? What happens when there is no one to generate our ARP request? In a situation where you have an access point with no wireless clients, we can often still crack the WEP key by using a different method. Aircrack-ng has two attacks, the correct chop-chop and fragmentation attacks, that can be used to crack the WEP key of a wireless network with no associated clients. The chop-chop and fragmentation attacks can both be used to obtain a PRGA bit file. Bear in mind, though, that the PRGA is not the WEP key and cannot be used to decrypt packets. However, it can be used to create new packets for injection. We will cover both of these attacks in this section, and the pros and cons of each attack are described more fully in the lab guide. Now, before I proceed with these attacks, I must confess that I'm growing weary of copying and pasting the various MAC addresses that we are using, so I will quickly set them up as environment variables in my .bashrc file. So I will run a little bash one-liner and export these as variables into the bashrc file. For var in, and we'll cat the info file. So this will take each entry in the info file and tail it to the bottom of the .bashrc file and set each entry as an environment variable. So now, in theory, with every new console window that I open, I will be able to reference these variables instead of copying and pasting the MAC addresses. Great, so let's move on. We begin, as usual, by starting our interface in monitor mode on the channel number of the access point with Airmon-ng start WLAN 03. Now we'll begin a new Airodump capture, also on channel 3, filtering on the BSS ID of our target access point, and save the capture to a file named WEP-frag. So I will enter in Airodump-ng -C3 --BSSID, and the variable of our access point, -W WEP-frag, followed by mon0. Great. So now we can see in the Airodump output that our access point is up and running, but there are no clients associated with it. In order to be able to communicate with the access point, we will need to conduct a fake authentication attack. As you will recall from the previous attacks, our fake authentication would time out after a period of time. So this time, we will run the fake authentication attack and provide an association timing so that our client will stay connected to the AP. So I'll open up a new terminal window, and I'll enter Aireplay-ng -1 for the fake authentication attack, and instead of 0 as we've entered before, I will enter 60. So every 60 seconds, Airreplay will reassociate to the access point. And -E waifu, the ESSID of our AP, -B, and the MAC address of the access point, -H, followed by our MAC address, again we use the variable, and mon0. Excellent. So looking at the Airodump output, we can see that our attack has been successful and we are now associated with the access point. And now, every 60 seconds, Airreplay will reassociate to the AP for us, keeping our session alive. So I'll just throw this console window to another desktop to keep things cleaner, and we'll carry on. The next attack we will cover is Airreplay's attack number 5, the fragmentation attack. The fragmentation attack does not recover the WEP key, but it obtains a PRGA keystream of the packet. The PRGA can then be used to generate packets with PacketForge-ng, which in turn can be used to generate packets for various injection attacks. The fragmentation attack requires at least one data packet to be received from the access point. Airreplay executes this attack by initially obtaining a small amount of keying material from the packet, and then attempts to send an ARP request packet with known content to the access point. If the packet is successfully echoed back by the access point, then the larger amount of keying information can be obtained from the returned packet. This cycle is repeated several times until 1500 bytes of PRGA are obtained. For more information on this attack, please refer to the lab guide. So let me just open up a new terminal window. And let's start the fragmentation attack by entering Aireplay-ng -5 to indicate the fragmentation attack, -b along with the MAC address of the access point, -h followed by our own MAC address, all through mon0. So at this point, we are waiting for a data packet, and once received, the fragmentation attack will actually begin. Alright, so let's choose this packet. Okay, so we managed to get a relayed packet, and we have our keystream file right here. Now if this attack doesn't work for you, keep a few tips in mind. The source MAC address used in the attack must be associated with the access point, so don't forget to do a fake authentication attack against the access point before running the fragmentation attack. Also remember that the fragmentation attack sends out a large number of packets, and these packets must all be received by the access point for the attack to be successful. If any of the packets are lost, then the entire attack fails. So this basically means that you need to have a good quality connection and be reasonably close to the access point. Now that we have obtained our PRGA file, let's take a look at PacketForge-ng and see what we can actually do with it. PacketForge-ng is a tool in the Aircrack-ng suite that can create encrypted packets, which can later be used for injection. To create an encrypted packet with PacketForge, you must have a PRGA file previously obtained from a WEP-enabled network. The PRGA is then used to encrypt the packet that you create. So let's try using our previous file from the fragmentation attack in order to create and then inject ARP packets into our network. We'll use PacketForge-ng in order to create our encrypted ARP request and then try to send it into the network. So we'll type in PacketForge-ng, and we'll specify -0 to create an ARP packet, -a followed by the MAC address of the access point, -h followed by our attacking MAC address, -l followed by the source address, and -k with the destination address. Now, the source address could plausibly be this address, and the destination address can basically be any address on the same network as long as it doesn't exist. I usually like to use the local broadcast address as it will never be an address assigned to a client. We will then add the -y parameter, followed by our PRGA XOR file name, -w, and the file name we wish to write the packet to. So I will call it injectme.cap. Now let's just check this file and see that it actually makes sense. We can do this using TCP dump. With TCP dump -n -vvv for extra verbosity, -e -s0 -r followed by our capture file. And based on the TCP dump output, we can see that the packet seems to make sense and appears to be healthy. Okay, so now we've got a nice ARP packet called injectme.cap. Let's try injecting this file into our live network and see if we can actually cause the access point to create new initialization vectors. To inject our newly created ARP packet into the network, we will use AirReplay's attack 2, the interactive packet replay attack. As you will recall from the end of the previous module, making use of a capture file with attack2 is very straightforward. So I will enter in Airreplay-ng -2 for the interactive packet replay attack, -r, followed by the capture file name, injectme.cap, and we will send this out through the Mon0 interface. We'll enter yes here to inject our crafted packet, and look at that! Our specially crafted packet is causing the access point to generate new IVs that we can then use to crack the WEP key. And we didn't even need to have a client connected to the access point. Now I won't actually crack the WEP key here, as we will next cover another technique for attacking a clientless network. Now that we have seen the fragmentation attack, let's take a look at Airreplay's attack 4, also known as the correct chop-chop attack. The correct chop-chop attack can decrypt a WEP packet without actually knowing the key. The attack performs a per-byte recovery of key stream for a given packet, which permits us to decrypt previous and future packets of equal or lesser length with the same initialization vector. This can then later help us to generate our own new packets for injection without the WEP key. We can actually use the correct chop-chop attack for various things. We can try to decrypt interesting packets in order to learn about the network. We can try to forge SNMP packets, or we can even do a blind port scan of the network. Most commonly, we'd like to use the correct chop-chop attack to surgically create an ARP request, with which we'll be able to accelerate our IV generation later on. One thing to bear in mind is that the correct chop-chop attack can't be used against every access point. However, it may work where fragmentation doesn't. For more information about the internals of the correct chop-chop attack and how it works, please refer to the lab guide. So let's try to implement the correct attack and figure out what it's all about. So I'll type in Airreplay-ng -4 for the correct chop-chop attack, -b followed by the access point's MAC address, -h followed by our own MAC address, and we send this through Mon0. Okay, so we're waiting for the right packet, and once one arrives, we'll ask Airreplay to try to decrypt it. So we've received a packet, so we'll type in yes here, and the correct attack goes into motion. I have edited out some of the long wait. You can see that the attack actually took just under 30 seconds to complete. And from the attack, we've received a decrypted packet and the PRGA source stream. So now we can do some interesting things with this information. Let's use tcpdump to view the decrypted packet by typing in tcpdump -s0 -n -e and -r, followed by the file name which contains the decrypted traffic. And looking at tcpdump's output, we can see that this is a broadcast packet, and we can even see the participating clients here. So the packet was sent from this IP address to this IP address. So we have actually verified the IP scheme of the network, and we've identified a real live client inside this network, all without knowing the WEP key. With this information, we can now go ahead and use PacketForge-ng to create an artificial ARP packet using our PRGA XOR file stream. Once we have our ARP packet, we can actually try to replay it into the network and hope that it causes IV generation. We have launched the correct chop-chop attack against our network. Let's try using the PRGA file in order to create and then inject ARP packets into our network. So let's just see what we have here. Alright, so these two files were generated by the correct chop attack. And if we remember correctly, we actually saw that this file contains an ARP request broadcast, which originated from the IP address 192.168.1.101. So now, we'll try using packetforge-ng in order to create an encrypted ARP request and then try to send it into the network. We'll run packetforge-ng again using the same syntax that we used earlier in this section with our fragmentation attack PRGA file. So I will enter in packetforge-ng -0 to create an ARP packet, -a, followed by the access point's MAC address, -h, followed by our own MAC address, -l, and the source IP address, -k, followed by the destination IP address, -y, followed by the file name of the PRGA file, -w, and the file name we wish to have for this packet. So now we have created an ARP packet called injectme2. Let's try injecting this file into the network and see if we can cause the access point to create new initialization vectors. Once again, let's use Airreplay-ng to inject our capture file. So I will enter in Airreplay-ng -2 for the interactive packet replay attack, -r, followed by injectme2.cap, our ARP packet file name, and we'll send this out through the mon0 interface. We'll select yes here to inject the packet. Excellent! So you can see that once again, we're managing to inject packets into the network, and the weak initialization vectors are increasing at a rapid rate. We should have captured more than enough IVs at this point to crack our access point's WEP key. So let's open up a new terminal and run Aircrack-ng against our running capture file and complete this module properly. So I will run Aircrack-ng -0 for the nice output, followed by our running capture file name. And once again, our simple WEP key has been cracked immediately. So in this module, we have shown that even when there are no wireless clients connected to an access point, we have two attacks at our disposal in order to recover the WEP key. To summarize these attacks, we began by placing our wireless card in monitor mode on our desired channel. With Airmon-ng, start WLAN 0, followed by the access point channel number. We then started a capture dump using Airodump-ng, saving the capture to disk. With Airodump-ng -c and the access point channel number, --BSSID, and the access point's MAC address, -w, and the capture file name, mon0. We then conducted a fake authentication attack against the access point with Airreplay-ng -1, 0, -e, and the AP ESSID, -a, and the AP's MAC address, -h, followed by our MAC address, mon0. We then launched Airreplay's fragmentation attack with Airreplay-ng -5, -b, followed by the AP MAC address, -h, and our MAC address, mon0. The syntax for the correct chop attack is identical, except that it uses attack 4 instead of attack 5. After we received the PRGA file from the fragmentation attack, we crafted an ARP packet using packetforge-ng by running packetforge-ng -0 to create an ARP packet, -a and the AP MAC address, -h, followed by our MAC address, -l, and the source IP address, -k, and the destination IP address, -y, followed by the XOR file name, -w, and the file name we wish to write the packet to. We then use the interactive packet replay attack to inject our newly created packet into the network with Airreplay-ng -2 -r and the packet file name through the Mon0 interface. And once we saw that the injection was successful, we launched Aircrack-ng and cracked the wireless WEP key by running Aircrack-ng -0 followed by the capture file name. Until now, we have been attacking our access point, which is configured for Open System Authentication. Open System Authentication allows any device to join the network, assuming that the device SSID matches the access point's SSID. Alternatively, the device can use the Any SSID option to associate with any available access point within range, regardless of its SSID. Shared key authentication requires that the station and the access point have the same WEP key to authenticate. So let's see how we deal with such a situation. But before we actually start hacking away, let's configure our access point for shared authentication. So I'll quickly switch over to my Windows XP client, and I will bring up the access point's administrative interface. I'll go to my wireless settings, and I will set my authentication type to shared key. And we will keep the same WEP key of AABBCCDDEE. So let's just save our settings. Now with Windows XP, we will need to change the advanced settings of our wireless card to enable it to use shared key authentication. So we'll just set the network authentication to shared and click OK. And we can see that we have connected successfully back to our network. So we should be good to go now. So let's switch back to our attacking machine. So just as a quick reminder, we're attempting to attack a WEP-enabled network which is using shared key authentication. So let's start with the usual routine and see what happens. I'll begin by putting my wireless card into monitor mode on channel 3. Airmon-ng, start WLAN 0, 3. Then I'll begin an Airodump-ng capture, filtering on channel 3 and on the BSSID of the access point, and we'll save the capture out to a file called shared key. Airodump-ng -C3 -BSSID $AP -W shared key Mon0. Now I'll attempt a fake authentication attack by running Airreplay-ng -10 for the fake authentication attack, -A $AP, our access point's MAC address, -H $mon, our MAC address, Mon0. And there, look at that. Look at what happened. We got a message stating that it had to switch to shared key authentication, as the access point does not allow open authentication. This therefore is further evidence that shared key authentication is being used on the access point. Let's take a quick look at a Wireshark capture to see what happened during our failed authentication attempt. In the first packet, we can see that we first attempted to authenticate via the open system. The access point responded with a message saying that the station does not support the open authentication. Our next packet then attempted to authenticate via shared key. The access point returned a code of successful indicating that it is indeed using shared key authentication. Our next packet attempted to authenticate with a shared key. But since the key was wrong, the access point rejected our authentication. So in order to perform a fake authentication to the wireless network, we need to overcome this issue. What we need to do is capture a PRGA XOR file as the client authenticates to the network. As we can see in the Airodump-ng output, there is no indication under the auth column that the access point is using shared key authentication. This column will not display SKA until a client authenticates. We can hurry this process along by de-authenticating the connected client using Airreplay's attack 0. So I will enter in Airreplay-ng -0, 1 for the de-authentication attack, -A $AP for our access point, -C $vic for the victim client, mon0. Wonderful. Now that the client has reconnected to the wireless network, Airodump displays SKA under the auth column. So now, if we do a directory listing in the root folder, we should hopefully see the shared key PRGA XOR file. And here we have it right here. Using this PRGA file, we can now conduct a shared key fake authentication attack. So I will run Airreplay-ng -160 for the fake authentication attack, reassociating every 60 seconds, -E WIFU, our access point's ESSID, -Y, followed by the file name of the PRGA file, -A and the access point's MAC address, -H and our MAC address, all through the mon0 interface. Perfect. So we can see that we have successfully conducted a fake authentication to the shared key network. So let's proceed with the rest of our attack. Now that we have successfully conducted our fake authentication attack against the AP, let's move on and run the ARP request replay attack, attack 3, against our target network. As we have covered previously, this attack will listen for an ARP packet, and once one is received, it will retransmit it back to the network, forcing the access point to generate new initialization vectors. So let me just move our fake authentication console over to another desktop, and then I'll run Airreplay-ng -3 for the ARP request replay attack, -B and the access point MAC address, -H and our MAC address, through the mon0 interface. And now we are waiting for an ARP packet to show up on the wireless network. So rather than waiting for this to happen naturally, we can run another de-authentication attack against the victim client. When it reconnects, it will very likely send an ARP request as it rejoins the network. So that's Airreplay-ng -0, 1, -A and the access point MAC address, -C and the victim MAC address, through mon0. Terrific. As the client rejoined the network, the ARP replay attack found an ARP packet and is retransmitting it back to the network, causing the access point to generate new IVs. We can see the data field increasing rapidly as the IVs are generated. With the ARP replay attack well underway, let's try cracking our access point's weak WEP key using Aircrack-ng. So I'll just open up a new terminal, and I'll run Aircrack-ng -0 to give us the nice colorful output, -z for the PTW attack, -n, 64, for the number of bits in the WEP key, and we'll provide it the name of our capture file. And once again, we have cracked our WEP key, this time against a wireless network running shared key authentication. Now let's review our attack from start to finish. We began by setting our wireless interface in monitor mode on the channel number of the access point, with Airmon-ng start WLAN 0 followed by the AP channel number. We also began sniffing the wireless network, filtering on the AP channel and BSS ID while saving the capture out to a file, with Airodump-ng -c and the access point channel number, --BSS ID and the access point MAC address, -w and the file name we wish to save it to, mon0. Then, in order to capture the PRGA XOR file, we de-authenticated the connected client, with Aireplay-ng -0, 1, -a and the AP MAC address, -c and the victim's MAC address, mon0. We then conducted a shared key fake authentication attack against the network using the PRGA file, with Aireplay-ng -1, 60, -e and the AP ESS ID, -y and the shared key XOR file, -a, the access point MAC address, -h and our MAC address, mon0. Next we ran Airreplay-ng's ARP request replay attack, with Airreplay-ng -3, -b and the AP MAC address, -h followed by our MAC address, mon0. To speed up the process of acquiring an ARP packet, we ran another de-authentication attack against the connected client, again with Airreplay-ng -0, 1, -a, the AP MAC address, -c, the victim MAC address, mon0. Once the victim reconnected to the network and we started injecting ARP packets generating weak initialization vectors, we ran Aircrack-ng and cracked the WEP key with Aircrack-ng -0, -z, -n, 64, followed by our capture file name. So far, we have been focusing on various methods of attacking WEP-enabled networks. Now we'll begin looking at cracking WPA networks. It's very important to note that all of the fancy injection techniques we have been discussing so far are not relevant to WPA-enabled networks. Although WPA-encrypted networks don't suffer from the same cryptographic vulnerabilities as WEP-enabled ones, they are still only as secure as the passwords used to protect them. Currently, the only feasible method for cracking the shared key of WPA-enabled networks is raw brute force. Basically, we need to capture the WPA pre-shared key when a client authenticates and then attempt a local brute force attack in order to try to crack the WEP key. Obviously, the longer the passphrase, the longer this can take, which makes this attack not very feasible for networks protected by very strong passwords. However, since users are not known for selecting strong passwords to protect themselves, it can actually be easier to crack WPA keys versus WEP ones. Before we begin, I'll need to configure my access point to use WPA encryption, so I'll switch over to my Windows XP client. And I'll bring up the AP's administrative interface. I'll go to my wireless settings, and I will set my security mode to WPA with a network key of password. Now I'll just save my settings, and I'll reconnect back to the network with the new password. Everything should be good to go now, so let's switch back to our attacking machine and get started. As usual, we will start off by putting our wireless interface into monitor mode on the channel of our access point with Airmon-ng start WLAN 0 3. To capture the WPA handshake as a client authenticates to the access point, we will run Airodump-ng, filtering on the channel and BSS ID of our AP, and save the capture to a file, with Airodump-ng -C3 --BSS ID, followed by the MAC address of our access point, -W, and we'll save this to a file called WPA -Mon0. And we can see in the Airodump output that our access point is now using WPA2 encryption with pre-shared key authentication. We can also see that our victim client is currently associated to the AP. Every time a client connects to a WPA-enabled network, it needs to authenticate using a four-way handshake. If we can capture this four-way handshake, we can then use Aircrack-ng to hopefully guess the WPA password. For more detailed information on the four-way WPA handshake, please refer to your lab guide. Now, since we know that the WPA four-way handshake takes place whenever a client connects to the wireless network, we can run a de-authentication attack against a connected client and try to capture the four-way handshake as it re-authenticates to the network. So let's give that a try. I'll run Aireplay-ng -0 1 -A and our access point's MAC address, -C and the victim's MAC address, Mon0. And as I execute this attack, let's keep an eye on the Airodump window. Airodump shows us up here at the top that a WPA handshake was captured for our target network. So let's stop the capture dump and take a brief look at a Wireshark capture to see the four-way handshake. These four packets make up the WPA four-way handshake. And the handshake consists of two pairs, which we can see in the replay counter field. If the pairs are not matching, then you have captured an incomplete handshake. In addition, packets 1 and 3 need to have the same nonce value. So again, if these do not match, you will need to retry the handshake capture again. So let's close out Wireshark and proceed with our attack. Now that we have captured the WPA handshake of our target network, let's try running Aircrack-ng against it and see if we can recover the WPA password. The techniques we used for cracking WEP keys will not work for WPA, so we will run Aircrack using its word list mode with the small word list provided with John the Ripper. So we'll run Aircrack-ng -0 -w for word list mode, and we'll provide the path to the John the Ripper word list under /pentest/passwords John and password.lst. And as always, we'll provide the name of our capture file. And just as easy as that, our simple WPA password has been recovered. Now obviously, this was an extremely simple password, so the more words you have in your word lists, the better your chances will be when attacking other wireless networks. Aerolib-ng is a tool designed to store and manage ESSID and password lists, compute their pairwise master keys, and use them in order to crack WPA and WPA2 passwords. WPA cracking involves calculating the pairwise master key, which is very slow since it uses the PBK-DF2 algorithm. However, the PMK is always the same for a given ESSID and password combination. This allows us to pre-compute the PMK for given combinations and speed up the cracking of the WPA handshake using Aircrack-ng. So we'll begin by placing our access point's ESSID into a text file. So echo waifu, and we'll push that into ESSID.txt. Then we'll import this file into Aerolib-ng's database. If the database doesn't already exist, it will be created for us. So I'll run Aerolib-ng, followed by our database file name. We'll call it testdb, --import ESSID, and the file name containing our ESSID list. So that's ESSID.txt. Now, if we pass the stats parameter to Aerolib, we can see that our ESSID has been imported successfully. So that's Aerolib-ng, followed by our database file name, testdb, --stats. At this point, we don't have any passwords stored in our database. So let's take care of that by importing the John the Ripper word list. I'll run Aerolib-ng testdb --import password and the path to our word list /pentest/passwords /john /password.lst. Aerolib-ng tells us that 2,500 invalid lines have been ignored in the word list. Many of the entries in our word list are not valid for use as WPA passwords, so they are not imported into the database. So now, to have Aerolib-ng generate the PMKs for us, we can use the batch parameter with Aerolib-ng testdb --batch. And now we can view the database stats again to confirm that everything is ready. Aerolib-ng testdb --stats. Excellent. The Aerolib output tells us that all possible combinations have been computed. So now we can use our newly created database and PMKs to crack our WPA password using Aircrack-ng. So I'll run Aircrack-ng -r, followed by our database name, testdb, and our WPA capture file name. And once again, although much more quickly this time, we have successfully recovered the WPA password. For more information on Aerolib-ng, please refer to your lab guide. In summary, we began by placing our wireless interface into monitor mode on the channel number of the access point, with Airmon-ng start WLAN 0 followed by the access point channel number. At this time, we also started a capture using Airodump-ng, filtering on the AP channel and BSS ID, saving the capture to a file by running Airodump-ng -c followed by the access point channel number --BSS ID and the AP MAC address -w and the capture file name mon0. To force a client to reconnect to the access point and complete the four-way handshake, we conducted a de-authentication attack with Airreplay-ng -0 1 -a and the access point MAC address -c and the victim MAC address mon0. And after the victim reconnected to the network and we captured the WPA four-way handshake, we proceeded to crack the WPA password using Aircrack-ng by running Aircrack-ng -0 -w followed by the path to the word list followed by the capture file name. Aircrack-ng is great at guessing WPA passwords. However, you need to have very large word lists in order to cover all possibilities. Using John the Ripper with an existing word list, we can take advantage of the different mangling rules that it has. For instance, if our word list includes the lowercase word of password, John the Ripper will try password with a capital P, password with a number at the end, etc. I have changed the WPA password of my access point to password123 with a capital P. So let's get started with our attack and see how this works. We will start, as always, by putting our wireless interface into monitor mode on channel 3. Airmon-ng start WLAN 0 3. And we'll also start our Airodump session to capture the WPA handshake as the client connects to the wireless network. Airodump-ng -c3 --BSS ID $AP -w, and we'll save this to WPA John mon0. Since the WPA four-way handshake takes place whenever a client connects to the wireless network, we'll run a de-authentication attack against our victim client so that we can capture the four-way handshake as it re-authenticates to the network. So let's give that a try. I'll run Airreplay-ng -0 1 -a $AP -c $vic mon0. Perfect. So Airodump-ng shows us that a handshake has been captured. So let's stop our capture here and move on to cracking the WPA password. Because running the John the Ripper word list rules can be computationally intensive combined with Aircrack-ng, we will use the small word list included with Aircrack. So we can see that there is one instance of the lowercase word of password, which, of course, will not work for guessing our WPA password. For this reason, we will use John the Ripper's word mangling rules to expand our word list. There is, however, an issue with the default rules, at least for the password I have currently set on the access point. Let's see what word mangling takes place when I run John the Ripper with the default rules. I'll just open up a new terminal window, and we'll change to the John the Ripper directory. And I'll run /John --word list equals /pentest wireless Aircrack-ng test password.lst --rules. This will tell John to use its word mangling rules. --std out. This will have John output the words to the screen. And let's grep for password 1. And look at that! By default, John the Ripper will only append 1 digit to the end of each word, whereas we need 3 digits. So let's overcome this issue by editing john.conf and add to the default rule set. So I'll just run nano john.conf. And we'll search for the word list rules. So this is where the word list mangling takes place. Let's just go to the end of it. And at the end of the list here, we will add 2 additional rules that will append 2 and 3 digits to the end of each word in the word list. So this will add 2 digits between 0 and 9 to the end of each word. And this rule will add 3 digits. So I will just exit and save this. And let's run the rules against our word list again, this time grepping for password 123, and let's see if it works. Perfect. So now, John the Ripper should be able to find our WPA password. Let's see how we can combine John the Ripper with Aircrack-ng to recover the password of our access point. So we'll run /John --word list equals /pentest /wireless /Aircrack-ng /test /password.lst --rules to use the default word mangling, --std out, and we will pipe this into Aircrack-ng with Aircrack-ng -0 -e waifu -w and another minus sign to accept John's output, and the name of our capture file, /root WPA John. Fantastic! We have successfully combined the word mangling rules of John the Ripper and the password guessing capability of Aircrack-ng to recover our access point's WPA password. I cut out a large chunk of the processing time, but we can see that John the Ripper took our word list of approximately 2,000 entries and had transformed it into over 400,000 entries by the time it found the password. With John the Ripper, we are not solely limited to word lists. For more information, please refer to your lab guide. To summarize this attack, we began by placing our wireless interface into monitor mode on the channel of the access point, with Airmon-ng start WLAN 0 and the access point channel number. At this time, we also started to capture using Airodump-ng, filtering on the AP channel and BSS ID, saving the capture out to a file, by running Airodump-ng -c, the AP channel number, --BSS ID, and the AP MAC address, minus W and the capture file name mon0. To force the client to reconnect to the access point and complete the four-way handshake, we conducted a de-authentication attack with Airreplay-ng minus 0, 1, minus A and the AP MAC address, minus C and the victim MAC address, mon0. Once the victim reconnected and we captured the WPA four-way handshake, we changed over to the John the Ripper directory with cd/pentest/passwords/John. Then, we piped in John the Ripper's mangled words into Aircrack-ng and cracked the WPA password by running /John --word list equals and the path to the word list --rules --std out. Then we piped this into Aircrack-ng -0 -e and the APESSID -w and then the path to the capture file name. To summarize this attack, we began by placing our wireless interface into monitor mode on the channel of the access point with Airmon-ng start WLAN 0 and the access point channel number. At this time, we also started to capture using Airodump-ng, filtering on the AP channel and BSSID, saving the capture out to a file by running Airodump-ng -c, the AP channel number, --BSSID, and the AP MAC address, -w, and the capture file name, mon0. To force the client to reconnect to the access point and complete the four-way handshake, we conducted a de-authentication attack with Airreplay-ng -0, 1, -A and the AP MAC address, -C and the victim MAC address, mon0. Once the victim reconnected and we captured the WPA four-way handshake, we changed over to the John the Ripper directory with cd/pentest/passwords/John. Then, we piped in John the Ripper's mangled words into Aircrack-ng and cracked the WPA password by running /John --word list equals and the path to the word list --rules --std out. Then we piped this into Aircrack-ng -0 -e and the APESSID -w and then the path to the capture file name. Cowpatty is a versatile tool that can recover WPA pre-shared keys using both dictionary and rainbow table attacks. Although it is not being actively developed, it is still quite useful, especially when using its rainbow table attack method. Cowpatty does not include a sniffer component, so we will still need to capture a WPA handshake using Airodump-ng. But before we do that, I will add the password for our access point to the end of the John the Ripper word list with echo password123, and we'll append this to /pentest/passwords/John/password.lst. Having our password at the end of the word list will give us a better indication of the speed of rainbow table attacks versus regular word list mode. So let's get started and see what Cowpatty has to offer. We will need to capture the four-way handshake, so let's quickly do that. I'll begin by putting my wireless interface into monitor mode, Airmon-ng, start, WLAN 0, 3. And I'll begin an Airodump capture with Airodump-ng -C3 -BSSID $AP -W, and we'll name our capture WPA cow Mon0. Now let's de-authenticate the connected client so we can capture the four-way handshake as it reconnects to the wireless network. So I'll run Aireplay-ng -0 1 -A $AP -C $vic Mon0. And according to the Airodump output, a WPA handshake has been successfully captured. So let's close out our capture and proceed to look at Cowpatty. We'll begin by first using Cowpatty in dictionary attack mode to give us something to compare against when we run the rainbow table attack later. Let me just open up a new console window. So we'll run Cowpatty -R followed by the name of our capture file, -F followed by the path to our word list, that's /pentest /passwords /john /password.lst, -2 for non-strict mode. Cowpatty seems to have an issue with Airodump's captures, so non-strict mode allows the capture to work with it. And we enter -S and the access point's ESSID, waifu. And after a very brief time, Cowpatty recovered the WPA password. And here, we can see that it tested over 126 passphrases per second, which sounds pretty fast. For the sake of comparison, let's use Aircrack-ng with the same word list. So that's Aircrack-ng -W and the path to our word list, /pentest /passwords /john /password.lst, and the name of our capture file. And here we can see that Aircrack-ng is much faster cracking passwords in word list mode, at over 755 keys per second. But that's okay, because Cowpatty really shines with its rainbow table attack. But before we can actually do a rainbow table attack using Cowpatty, we first need to generate the tables. Cowpatty includes a tool, GenPMK, that can do this for us. An important point to bear in mind with WPA tables is that they need to be generated for each unique ESSID. The ESSID is combined with the WPA pre-shared key to create the hash, so the hashes for the ESSID of waifu would not be the same as those for Linksys or D-Link. So let's generate a set of hashes for our John the Ripper word list. I'll enter in genpmk -f and the path to our word list, -d and the file name we wish the hashes to be saved to. We'll call this waifu hashes, -s, followed by the access point's ESSID, waifu. And after a short time, genpmk finishes, and we have our set of WPA hashes. So let's try running Cowpatty against our capture file again to see the difference in speed. I'll run Cowpatty -r, followed by the capture file name, -d, and the file name of our rainbow table, waifu hashes, -2, again for non-strict mode, -s, and the access point ESSID, waifu. And look at how much faster that was. Cowpatty tested passphrases at a rate of over 78,000 per second. This is the great benefit with rainbow tables, since all of the computation is done in advance. Before using Cowpatty to retrieve the WPA password, we first needed to capture a WPA handshake. So we began by placing our wireless interface into monitor mode with Airmon-ng start WLAN 0 followed by the access point channel number. We also started an Airodump capture with Airodump-ng -c and the AP channel number -BSSID and the AP MAC address -W and the capture file name mon0. We next de-authenticated the connected client by using Airreplay-ng -0, 1, -a and the AP MAC address -c and the victim MAC address mon0. Once the victim reconnected to the AP and we captured the four-way handshake, we ran Cowpatty in word list mode with Cowpatty -r and the capture file name -f and the path to the word list -2 for non-strict mode -s followed by the access point ESSID. Then, before we could run Cowpatty using a rainbow table, we first generated the WPA hashes with genpmk -f and the path to the word list -d and the output hashes file name -s followed by the AP ESSID. After the WPA hashes were successfully generated, we launched Cowpatty using the newly created tables instead of a word list by running Cowpatty -r and the capture file name -d and the hashes file name -2 for non-strict mode -s followed by the AP ESSID. Like Cowpatty, Pirate relies on the creation of pre-computed databases of WPA pre-shared key tables. Not only can it make use of regular CPU processing power, it can also leverage the extra power of GPUs to further accelerate the table generation. Pirate can read in packets from a raw or compressed packet capture file, or even from an interface, so it isn't necessary to use an external application to capture a four-way handshake as you do with Cowpatty. So let's see what exactly we can do with this versatile tool. I'll start as usual by putting my wireless interface into monitor mode. Airmon-ng, start WLAN 0, 3. Now, even though Pirate can use our monitor mode interface to capture traffic, it does not filter by BSSID, so we will start an Airodump capture to ensure that we only capture the traffic from the access point we are interested in. So as usual, we will run Airodump-ng -C3 --BSSID $AP -W, and we'll save this to WPA Pirate Mon0. To give Pirate something to work with, I'll run a de-authentication attack against the victim wireless client using Airreplay-ng. Airreplay-ng -0, 1 -A $AP -C $VIC through Mon0. And our Airodump output shows us that the four-way handshake has been captured. So let's stop our capture here and move on to explore Pirate and some of its many features. Hopefully, our capture file contains a proper four-way handshake. We can use Pirate's analyze command to parse the capture file and determine if any handshakes are present. So I'll run Pirate -R followed by our capture file name and analyze. And we can see that we have indeed captured a WPA handshake. And Pirate displays the access point BSSID, ESSID, and client MAC address that completed the handshake. Raw capture files contain all of the wireless data that was seen by the sniffing interface while the capture was running, so they often contain a great deal of extra data that we are not concerned with when trying to recover the WPA password. As you will recall from earlier, the four-way handshake only consists of 4 packets that can be buried in a capture containing thousands of packets. Fortunately, Pirate contains a nice feature that will remove all of the excess data from a capture file, saving only the handshake data we are looking for by using the strip command. So we'll run Pirate -R followed by the capture file name -O and the output file name. We'll use WPA stripped and the strip command. So Pirate took our original capture file and saved only the packets we need to crack the WPA pre-shared key. And we can see that the size now is only 916 bytes versus over 178,000 bytes of the original capture file. So now, let's use the basic dictionary attack with Pirate to get a baseline idea of cracking speed without using pre-computed tables. So I'll enter in Pirate -R and our stripped file name, -I and the path to our word list, /pentest, /passwords, /john, /password.lst, -B, $AP for our access point, and attack_passthrough. In mere seconds, Pirate has returned the password of our access point, and it processed at a speed of 330 PMKs per second. Now this sounds quite fast, but it is still nothing in comparison to the speed we can obtain by using pre-computed hashes. So let's try that next. It stores all of its pre-computed hashes in a database that can grow up to millions of entries. If your Pirate installation is fresh, the database is likely empty. We can see what the database status is by using the eval command. So we simply run Pirate eval. Since I have a fresh Pirate installation, there are no passwords in the database, so let's do something about that. I'll import the John the Ripper word list using Pirate -i, followed by the path to the word list file, /pentest, /passwords, /john, /password.lst, followed by import_passwords. Now, if we run Pirate eval again, Pirate now shows that it has 490 passwords available in its database. Notice how this number is lower than the actual number of passwords in our word list. This is because not all of the entries in the word list we used are valid WPA passwords, so Pirate only stores the usable ones in its database. We next need to add an ESSID to the database, so I will run Pirate -e waifu, our ESSID, followed by create_ESSID. So now we have enough information stored in the database to start creating the pairwise master keys using the ESSID and passwords. We can do this by running Pirate followed by batch. Now everything is all set for our attack using Pirate's database, so let's run it against our capture file and see just how much faster it is compared to the basic dictionary attack. I'll run Pirate -r, followed by our stripped capture file name, and attack_db. And look at how much faster that was compared to the dictionary attack. Although we only had a small word list, the speed increase was still significant, with over 40,000 PMKs being tested per second when using the database. Perhaps the best feature of Pirate is its ability to use GPU power in order to crack WPA passwords. GPU technology has advanced a great deal, and they have immense processing power, power which can be harnessed to perform computationally intense tasks. I have remotely logged into another server that is solely built for GPU-powered cracking. This will give us the opportunity to see how much faster GPU cracking is versus CPU cracking. We'll start by listing the cracking cores that are available to Pirate with Pirate list_cores. This computer has 3 dual-core GPUs, along with a dual-core processor, and Pirate will use all 8 of these cores when cracking WPA passwords. Let's run a benchmark test to see what kinds of speeds we can obtain with GPU-powered cracking. We can do this by running Pirate benchmark. And Pirate's benchmark test shows us that we can test passwords at over 60,000 PMKs per second. It also shows the significant speed of GPU-powered cracking versus CPU-powered cracking. By way of comparison, running the benchmark test on the computer we have been using up to this point only results in a speed of just over 1,300 PMKs per second. So if you have the option to use GPU power, it is certainly well worth it. I have copied over our stripped WPA handshake capture file and a much larger word list. This password list has over 1.7 million entries, compared to just over 3,000 entries in the default John the Ripper word list. So let's see what GPU cracking is all about. We'll begin by ensuring that we are starting with a clean slate by running pirate eval. At this point, we have an empty database, so I will start by importing our new word list with pirate -i, followed by the name of our word list, import underscore passwords. I will also need to add an ESSID to our database. We can do that by running pirate -e waifu create underscore ESSID. Our database now has enough information for Pirate to compute the pairwise master keys using our imported word list along with the access point ESSID. So now, let's create our PMKs by running pirate batch. To provide a further idea of just how fast GPU power is, processing this same word list and ESSID on our regular machine took over 5 minutes to complete. Now we have everything we need to use Pirate to recover our WPA password from the capture file. So I will run pirate -r, followed by our capture file name, WPA stripped, and attack underscore DB. And in the blink of an eye, our password has been recovered, and Pirate was testing PMKs at an obscene rate. It can't be stressed enough just how fast and powerful GPU cracking is. If you have the ability to use it, it is very wise to do so. Recap our attack. We first needed to capture a WPA 4-way handshake, so we started by placing our wireless card into monitor mode with Airmon-ng start WLAN 0 followed by the access point channel number. At this point, we also began an Airodump capture by running Airodump-ng -c and the access point channel number --BSSID and the AP MAC address -w and the capture file name all through Mon0. We next de-authenticated a connected wireless client with Airreplay-ng -0 1 -a and the AP MAC address -c and the victim MAC address through Mon0. Once the client reconnected and we captured the WPA handshake, we used Pirate's dictionary mode to recover the WPA password by running pirate -r followed by the capture file name -i and the path to our word list -b and the AP MAC address attack underscore passthrough. After successfully retrieving the password using dictionary mode, we then proceeded to use database mode in order to compare the differences in speed. We first imported the John the Ripper word list with pirate -i followed by the path to the word list import underscore passwords. Then we added an ESSID to the Pirate database by running pirate -e followed by the AP ESSID create underscore ESSID. With our passwords and ESSID imported into the database, we had Pirate generate the PMKs for all combinations by running pirate batch. And finally, we launched Pirate in database mode to crack the WPA password with pirate -r followed by the capture file name attack_db. Once you have successfully retrieved the key to a wireless network, you can use Airdecap-ng to decrypt WEP, WPA, or WPA2 capture files. It can also be used to strip the wireless headers from an unencrypted wireless capture. Let's start exploring Airdecap-ng by first removing the wireless headers from an unencrypted wireless capture file. I'll first open up the capture file in Wireshark so that we can see what it looks like. In the default wireless capture, we can see a great deal of probe responses and other packets that we are not particularly interested in. So now let's use Airdecap-ng to strip out the wireless headers in our capture file. I'll run Airdecap-ng -b $AP and the name of our capture file. The file name ending with -dec.cap is the stripped version of our original capture file. So let's take a look at it in Wireshark. Now, in our stripped version of the same capture file, we only have the interesting traffic that appeared on the network. Now let's use Airdecap to decrypt a WEP-encrypted capture file. Again, we'll first open the capture file in Wireshark. Without the WEP key, the capture file does not provide us with any useful information. When we can see that the data fields are completely encrypted. So let's use Airdecap and decrypt it using our previously obtained WEP key. So I will run Airdecap-ng -w followed by our WEP key AABBCCDDEE and the name of our capture file. And if we open up the decrypted capture in Wireshark, we should see a large difference. Excellent! Airdecap-ng has decrypted our capture file perfectly, and now all of the data that was obfuscated is now completely visible to us. Lastly, let's decrypt a WPA2 capture file. I won't bother opening up the encrypted version in Wireshark, since it will largely be the same as our WEP-encrypted capture. We can decrypt the capture file with Airdecap-ng -e waifu, the ESSID of our access point, -p followed by the WPA password, and the name of our capture file. Now let's open up this decrypted file in Wireshark. And once again, the once encrypted wireless traffic is now available to us in clear text for further analysis. As these examples show, wireless pen testing does not simply end with recovering the keys or passwords. There is a wealth of information traveling through the airwaves that we can harvest data from. Airserv-ng is a fantastic tool included in the Aircrack-ng suite. It is a wireless card server that allows multiple wireless applications to use a wireless card across a TCP network connection. Airserv-ng can be useful in many situations. For example, you can easily deploy wireless sensors across your network or even around the world and access them remotely. When starting Airserv-ng, it listens on a specific IP address and TCP port 666 by default. The user on the remote computer can then use any tool in the Aircrack suite to connect to the server using the IP address and port number instead of a wireless interface name. To begin using Airserv-ng, we still need to have our wireless interface in monitor mode, so let's do that. Airmon-ng, start, WLAN 0, 3. We can then run Airserv-ng to serve up our Mon0 interface on the network. With Airserv-ng -P 1337 to specify port 1337 to serve on, -C3 for channel 3, -D for device Mon0. And we can see in the Airserv output that the server is now listening on port 1337 on our external IP address. So I will switch to the other terminal window and run Airodump-ng, connecting to the wireless card served over the network. So I'll run Airodump-ng -C3 -BSSID $AP, and now instead of Mon0, I will enter the IP address, a colon, and the port number that the server is listening on. And just as easy as that, we are sniffing the wireless network using a TCP connection instead of an interface directly. Airtun-ng is a virtual interface creator that allows encrypted wireless traffic to be decrypted in real time and made available to us on the tunnel interface. This capability is extremely useful in situations where we would like to implement a wireless intrusion detection system where we would need to monitor unencrypted traffic in real time. Of course, to implement such a scenario, we need to know the BSSID and encryption key of the wireless network. Once the tunnel is up and decrypting traffic, the tunnel interface can be used with external tools such as Wireshark or Snort. Airtun is also capable of injecting arbitrary traffic into the network, bidirectionally if you have the full encryption key, or outgoing unidirectional if you only have the PRGA file. The main advantage of Airtun-ng over other injection tools in the Aircrack-ng suite is that you can use any tool to subsequently create, inject, or sniff packets. Another nice feature of Airtun-ng is that it can also act as a repeater and provide TCP replay type functionality. The repeater function allows you to replay all sniffed traffic through a wireless device and optionally filter the traffic by BSSID and a network mask and replay the remaining traffic. Let's take a look at the wireless IDS functionality of Airtun-ng. I'll begin by first placing my wireless interface into monitor mode on the channel of our access point. With Airmon-ng, start, WLAN 0, 3. Now, if I try sniffing on our Mon0 interface, all we'll see is encrypted traffic. Let's take a look at that. I'll run Wireshark, and I'll start sniffing briefly on the Mon0 interface. Now we can see many beacons, but let's take a look at a data packet here. As expected, the data is completely encrypted. So let's close this out and see what Airtun can do for us. I'll start up Airtun by running Airtun-ng -A $AP, the MAC address of our access point, -W, and the access point's WEP key, AABBCCDDEE, and the Mon0 interface. Alright, so everything seems to be set up properly, and Airtun has created a new interface for us, AT0, so let's bring it up. And I'll run Wireshark again and start sniffing on the AT0 interface. And look at that! The data packets are now decrypted for us on the WEP-enabled network. So this AT0 interface could then be passed to a tool like Snort to implement a wireless intrusion detection system. For more examples on the uses of Airtun-ng, please refer to your lab guide. Airgraph-ng is a Python script that creates graphs of wireless networks using the CSV files that are generated by Airodump-ng. The CSV file generated by Airodump contains the relationships between wireless clients and access points, and can be passed to Airgraph-ng to create two types of graphs. The first type of graph is the client-to-AP relationship, or CAPR. It displays the relationships between the clients and access points, and therefore, any access points that do not have associated clients will not be drawn. We can generate a CAPR graph by running Airgraph-ng -I and the file name of the CSV file, -G and our graph type, CAPR, -O and the output file name. Let's open up the graph and see what we have. Airgraph-ng applies different colors to the access points depending on their type of encryption. The green access points have WPA encryption. The yellow access points are WEP-encrypted networks. Red access points have no encryption at all. And the black access points have an unknown encryption. So let's close out this graph and generate the second type of graph. The second graph, the Client's Probe Graph, or CPG, displays the relationships between wireless clients and probed access points. So even if a particular AP is not in the vicinity, they will still be drawn by Airgraph-ng. We can generate this graph by running Airgraph-ng -I and our CSV file name, -G and the graph type of CPG, -O and our output file name. And I will open up this graph and see what's there. So we can see the access point names that were being probed for by different wireless clients. Knowing what probes are being sent out by wireless clients can be very useful for setting up rogue access points, which we will be covering later on. Kismet is an incredibly versatile and feature-rich wireless network detector, sniffer, and intrusion detection system. Like Airodump-ng, it identifies wireless networks by passively sniffing the air and detects named networks, decloaks hidden networks, and detects the presence of non-beaconing networks via data traffic. Kismet sniffs A, B, G, and N networks and outputs logs in standard PCAP format for later use with external tools. It has a client-server architecture, multi-card and channel hopping support, and much more. The best way to get an idea of some of the many features of Kismet is to see it in action. So I'll run Kismet, and when we launch Kismet, we receive a warning stating that running it as root is dangerous, so I'll just press Enter to acknowledge this warning. We are next prompted to start the Kismet server. If you wanted to connect to a remote Kismet server, you would select No here, but since we want to run Kismet locally, I'll just press Enter to have the server started automatically. And I'll press Enter again to accept the server defaults. This is the Kismet server console where we can see the Kismet log messages. Since we don't have a GPS receiver connected to this computer, you can see the connection errors related to GPSD. So I'll just tab over and close out this window. And this is the main Kismet window, and we can see that right now it's not terribly interesting. This is because I haven't yet configured a capture interface. So let's do that now by selecting Kismet, Add Source. I'll enter in WLAN0 for the interface and name values, and then select Add. Kismet will automatically place the wireless card into monitor mode for us. Now this is much better. Kismet has already detected multiple wireless networks in my area, and near the bottom of the display is a graph showing the packets and data that are being detected. We can click on any wireless network in Kismet's list to display more detailed information about the network. In this new window, Kismet displays a great deal of information that it has gathered about the wireless network, and displays a packet graph at the top of the display. Let's just close out this window now. With our network still highlighted, we can see in the pane just under the network list the wireless clients that are currently associated. And similar to the output produced by Airgraph-ng, Kismet color codes the networks based on the encryption type that is detected. Green networks have no encryption, red networks are WEP encrypted, and yellow networks are WPA encrypted. Kismet also has a number of sort and view options that you can explore to tailor Kismet's display to your liking. Let's just close out Kismet now, since the best way to learn it is really to experiment and play with it on your own. So I will quit and kill the Kismet server. All of these files are generated by Kismet and contain a wealth of data that can be imported into other applications for further analysis. For example, the .net.txt file contains all of the detailed data about every network that Kismet detected. Here we can see a probe request that came from the wireless client looking for our wireless access point. And in this section, we have the beacons that were sent out by the wireless AP. The .pcap dump file is in standard pcap format, and so it can be opened in Wireshark. So again, we have a great deal of data that is at our disposal for further analysis. This was just a brief overview of Kismet, and the best way to get truly comfortable with it is to start using it and explore its many options. GisKismet is a very useful tool that allows us to use the data gathered with Kismet coupled with a GPS receiver and generate Google Earth compatible KML files. GisKismet stores the data from Kismet's netXML files in an SQL database, so you can use SQL queries to filter out specific information to display. So let's take a look at GisKismet and see what we can do with it. For starters, we will need a GPS receiver connected to the computer, so I will just plug mine in. Now by default, the receiver will be detected automatically and GPSD will be started. However, I prefer to have debugging output available to me, So I will find and kill the existing GPSD process. And let's just kill the existing process. Now I'll start up GPSD manually by running GPSD -n. This tells GPSD not to wait for clients before polling. -N to keep GPSD in the foreground. -D4. This sets the debugging level to 4. And then we pass the path to the device. Bear in mind that your device name may be different. I don't see any errors in the debugging output, so now I'll launch Kismet and get it configured. I will start up the Kismet server with the defaults. We will define a packet source. And in the Kismet server console, we can see that Kismet has detected the GPS device and is sniffing networks properly. So now it's time to take a drive. So I will just pause this and come back. My little war driving trip is complete, so let's just see what we have here. This Kismet netxml file contains the information that GisKismet needs in order to map out the access points that were detected. So let's begin by importing this file by running GisKismet -x to specify the netxml format, followed by our file name. And we can see all of the detected access points being added to the SQL database. Now let's generate a KML file containing all of the access points that were visible. So I will run GisKismet -q for query, and we will run a SQL query of select star from wireless -o, and we will specify an output name of all APs.kml. And I will open up this file using Google Earth, which I installed earlier. Look at the incredible amount of access points that were seen on this very short drive. We can also click on any of these APs to get more detailed information about them. We can see the BSSID, encryption in use, and even the connected clients. While fascinating, this does make for quite a cluttered display, so I will just remove this file from Google Earth. And I'll create another KML file and show only WEP-enabled networks with GisKismet -q, again for query, select star from wireless, where encryption equals, and then in single quotes, we'll enter in WEP in all capital letters. We'll just close out the query, and we will output this into a file called WEP-APs. So let's open up this file and see what we have. There, that's a much more manageable display. Although admittedly, it's truly sad to see that so many people still haven't gotten the message that web encryption is not safe at all. This was just a brief look at GisKismet. Not only is it practical, it's also quite fun, and you can create much more detailed SQL queries than the ones we covered here. Airbase-ng is a multi-purpose tool designed to attack clients as opposed to the access point itself. Among some of its many features is the ability to implement certain wireless attacks, cause the WPA handshake to be captured, act as a full access point, manipulate and resend packets, and more. The main idea behind using Airbase-ng is that it should encourage wireless clients to associate with the fake AP and not prevent them from accessing legitimate ones. It is important to note that Airbase-ng can very easily disrupt real access points nearby, so it is recommended that you use filters to minimize its impact. When wireless clients send out probe requests for previously configured networks, the fake Airbase-ng access point will respond to any probe request with the proper probe response that tells the client to authenticate to the Airbase BSS ID. Again, this mode of operation can potentially disrupt the functionality of many APs on the same channel. Let's take a look at some of Airbase-ng's many features. To begin with, we'll need to place our wireless interface into monitor mode. With Airmon-ng, Start, WLAN 0, and I'll configure it for channel 3. Now we can use Airbase-ng to set up a basic fake access point with Airbase-ng -C3 for channel 3, -E, and the ESS ID we wish to broadcast, we'll call it free Wi-Fi, and we'll use the Mon0 interface. Let's quickly switch over to our Windows XP client. And under Windows XP, we can see our fake access point appears in the list just like any other AP. And our wireless client can then connect to it just like any other AP. And our Airbase output shows us that the client has associated to our unencrypted wireless access point. By itself, though, this fake AP doesn't do much of anything useful. So let's shut down this instance and look at a far more interesting feature. We can actually use Airbase-ng to help us in capturing the WPA handshake of a wireless client trying to connect to a WPA encrypted network. I'll start by running an Airodump capture with Airodump-ng -C3 -D $mon. This will tell Airodump-ng to only save the data from our Mon0 interface. -W, and will save the capture to Airbase, all through Mon0. And we can see right now that Airodump-ng does not detect our wireless access point because we have not started it yet. Now let's set up our fake access point with Airbase-ng by running Airbase-ng -C3 for channel 3 -E waifu, the ESS ID we wish to broadcast, -Z4 to specify the WPA2 CCMP cipher, -W1. This forces the beacons to specify WEP encryption, since some wireless clients get confused without it. And we'll send this through our Mon0 interface. So now in our Airodump window, we can see that our fake access point looks just like the legitimate one. We can see in the Airbase display that the client is trying to associate. So I'll switch over to my XP client and try connecting to this network. An unsuspecting user would think nothing of entering in his WPA password, since the AP looks just like the one that he would be used to. So I'll click Connect, and switch back to our attacking machine. And look at that! we see that Airodump has captured a WPA handshake from the wireless client. So I'll open up a new terminal window and see if we can crack the WPA password. So I'll run Aircrack-ng -w and the path to our word list /pentest/passwords/john/password.lst and the name of our capture file. And just as easy as that, we have captured the WPA password without the real access point being anywhere near us. The ability to serve up rogue access points opens up a wealth of potential attacks, with the only limitation being your imagination. It is well worth exploring the many features that Airbase-ng has to offer. Metasploit is one of the most sinister attack vectors available when it comes to wireless networking. It uses a combination of the Karma attack, the Aircrack-ng suite, and the Metasploit exploitation framework. Karma takes advantage of the insecure nature of wireless clients by responding to all probe requests sent out by wireless clients. Once a victim client is associated with the malicious access point, attacks can be launched against it. As you will recall from earlier, we can use Airbase-ng to act as an access point, and it will respond to all beacons when configured to do so. Metasploit takes this attack to the next level by launching a wide variety of man-in-the-middle attacks and exploits at the client once it connects to the malicious access point. Let's get started and see what Metasploit is capable of. I will first need to install a DHCP server from the repositories, so I'll quickly do that. apt-get install DHCP3-server. It's perfectly safe to ignore the message about the server failing to start, so we will just proceed. I will next place my wireless interface into monitor mode on channel 3. Airmon-ng start WLAN 0 3. And I'll then start up our malicious access point with Airbase-ng -C3 to broadcast on channel 3, -P to respond to all probe requests regardless of ESSID, -C60 to rebroadcast the ESSIDs every 60 seconds, -E with the ESSID of free Wi-Fi, -V to display verbose output, all through the Mon0 interface. Our malicious access point is up and running, and it is already responding to probe requests. Airbase-ng creates a new interface for us, AT0, that we will need to bring up and assign an IP address to. So I'll run ifconfig AT0 up with the IP address of 10.0.0.1 with a /24 netmask, and hit enter. Directory for the DHCP server PID file and change the ownership of the directory to DHCPD. So I'll run mkdir -p to create the parent directories if necessary, /var/run/DHCPD. And we'll change the ownership by chown -R to recurse DHCPD:DHCPD for the user and group of DHCPD, and our PID directory /var/run/DHCPD. And we also need to create an empty DHCP leases file. So I'll just type in touch/var/lib/DHCP3/DHCPD.leases. Our malicious access point needs to be able to serve out IP addresses via DHCP, so we'll create a dhcpd.conf file containing the following. This configuration file contains everything our DHCP server needs, so we'll shove this into a temporary configuration file rather than overwriting the default one. So I will cat the file, and we'll shove this into /temp/dhcpd.conf. The final configuration step for our DHCP server is to create an empty log file and change the ownership of it to DHCPD. So I will touch /temp/dhcp.log, and we'll run chown dhcpd :dhcpd for the user and group again, /temp/dhcp.log. Now we are finally ready to start the DHCP server by running dhcpd3 -f to run the server as a process, -cf and the path to our config file, /temp/dhcpd.conf, -pf, followed by the path to the PID file, /var/run/dhcpd, /pid, -lf, and the path to our log file through the AT0 interface window. And I will download the Metasploit resource file from the Metasploit website. The Karma resource file contains a large number of commands that MSF console will run automatically when it is started, including exploits, auxiliary, and denial of service modules. We need to make a minor edit to this file, though, before we use it. Metasploit no longer supports the SQLite 3 database, and it has Postgres database support built in, so we just comment out the first 2 lines. And we'll exit and save. Now, at long last, we can launch MSF console using the Karma resource file. So I'll run MSF console -r and the path to our resource file, /root/karma.rc. That long string of output shows the progress of the dozens of modules that are being loaded and configured for us automatically. So all that remains now is for a wireless client to connect to our malicious access point. XP victim has automatically connected to our access point since it was previously configured to connect to the free Wi-Fi access point. Let's switch over to it and see what's going on. Nothing immediately appears out of the ordinary, but watch what happens when I open up Firefox. We have what appears to be a captive portal that is commonly seen on free wireless networks. The browser, though, is unresponsive. So let's switch back to our attacking machine and see what we have. It appears we have a Meterpreter shell. Let me just interact with it to be sure. Amazing! Our victim machine has been compromised simply by powering on the computer and opening up a web browser within range of our attacking system. For this very reason, it is very good practice to always deselect the option to remember wireless networks, as this auto-connecting behavior is present in virtually every operating system. We saw just how effective Metasploit can be, but what if we don't want to be quite so obvious that we're attacking the wireless network? What if we'd like to be a little more discreet and sinister? This is where a properly configured man-in-the-middle attack comes into play. As we saw in the Airbase-ng and Metasploit sections, when a victim client connects to our AP, they don't have any outside network connectivity. However, if we set up our environment correctly, we can make our attack completely transparent to the victim while having complete access to all of the wireless traffic. Let's take a look at how this works. I'll begin by placing my wireless card into monitor mode on channel 3. Airmon-ng, start, WLAN 0, 3. Then I'll set up a soft AP using Airbase-ng with Airbase-ng -C3 -E and the ESSID we'd like to broadcast. I'll call it free internet. Using our Mon0 interface. So at this point, a wireless client will be able to connect to our access point, but they really won't be able to do anything. So what we next need to do is create a new bridge interface and add our wired interface, ETH0, and the AT0 interface created by Airbase-ng. I'll create the new bridged interface by running brctl add br to add a bridged interface, and we'll call our interface name Hacker. Then I'll add our two interfaces to the new bridge. With brctl add if to add an interface, followed by the bridge name of Hacker, and I'll add the ETH0 interface. And now the AT0 interface. Now we'll need to assign IP addresses to the three interfaces and bring them all up. So that's ifconfig, ETH0, and we'll use an IP address of all zeros, and we'll bring it up. And I'll do the same thing with the AT0 interface. And for the bridged interface, we'll need to assign it a valid IP address for the wired network. ifconfig hacker will assign it the IP address of 192.168.1.8, and we'll bring this up. Perfect. Lastly, and this is where our man-in-the-middle transparency comes in, we need to enable IP forwarding on our attacking machine. So I will echo 1, and we'll direct this into /proc, /sys, /net, /IPv4, /IP_forward. So now, when a victim client connects to our access point, it will receive an IP address via the wired network, and all of its traffic will enter from the AT0 interface created by Airbase-ng and flow out through our ETH0 interface connected to the wired network. This places us in the middle of everything the user does on the network and is completely transparent. So let me switch over to my XP client and connect to our malicious access point. I'll refresh the network list, and here is our AP. So we have received a valid IP address of 192.168.1.237 from the wired network. Let me just ping Google to make sure everything is working properly. Now I'll switch back over to my attacking system, and we'll get a bit of an idea of what we can do with this attack. Let's begin with DriftNet. DriftNet is an interesting application that sniffs on our interfaces and displays any images that are loaded. It's not necessarily useful in this situation, but it really displays the effectiveness of this attack. So to run DriftNet, all I need to enter is DriftNet at the command line. Again, I'll switch back over to my XP system, and I'll browse to google.com. Everything seems perfectly normal as far as the client is concerned, but let's take a look at our attacking system again. And here in DriftNet's window, we can see that it has sniffed all of the images that were loaded by the victim. So this is all well and good, but let's see what else we can do. Let's load up Ettercap and start unified sniffing on our bridged interface. So I'll run Ettercap minus capital G. This will give us the GTK interface. And I will select Sniff, Unified Sniffing, and I will select the Hacker interface. I'll just resize this window and then start sniffing. Now I'll change back over to the XP system and connect to an FTP server located on the internet. And again, everything is behaving just as it should. So if everything worked properly, we should have captured the credentials in Ettercap. So let's take a look. And look at that. Ettercap has sniffed the FTP credentials successfully. And just like that, we have stealthily placed ourselves in the middle of all client traffic. Naturally, we'll be able to capture the credentials of any clear text protocol with this attack. There are a wide array of attacks you can launch against your victim clients once you control all of their traffic. You are limited only by what you can think of. This concludes the video portion of the course. The world of wireless hacking is quite vast and ever-changing, and it's simply not possible to cover each and every avenue of attack. Hopefully, we have piqued your interest in the realm of wireless penetration testing and have armed you with the skills and techniques to further explore this fascinating field.